Good morning, everybody. Glad you could all join me here today. Abigail just covered the sediment side of the story, and I'm going to do something I don't normally like to do, and that's focus on the bedrock. So just very quickly, multiple ice ages have affected Ontario's landscape, and generally speaking, they locally deposited huge piles of sediments, and they eroded the bedrock significantly and created a lot of features on the bedrock. And at the OGS, our primary focus is looking at that sediment pile, understanding the sediment layers in excruciating detail at times, and helping you folks get a better understanding of their regional distribution, and so we can have a better predictive power to understand water flow. Having said that, we're starting to realize that we might have been missing something by not ignoring the erosional side of the story, but having such a strong focus on sediment deposition. And when we started looking at the rock surface, there might be something pretty interesting going on. And that's what we're going to talk about today. So I know it's unfortunate that we don't have all glaciologists and quaternary folks here, so we're going to do a quick crash course on glacial erosion, and it'll be very heavy on pictures. So when I talk about glacial erosion, we normally think about three things. The first is abrasion. That's when the ice is dragging hard material and it's scraping across the bed, creating little scratches and very small streamline forms. There's plucking, when water and ice gets inside pre-existing fractures in the rock, and then it expands and it rips up intact blocks and they retain their prominent shape. And then there's meltwater erosion. And so meltwater is under high pressure with lots of sediment, and it can carve very beautiful and impressive features like the one I kayaked into along the French River. And in lots of areas, all three of those processes are happening at the same place and roughly at the same time. So this is a nice example from the eastern shore of Georgian Bay, where the upper surface of this rock you're seeing is beautifully streamlined and striated. But then everything below that black line, you can see all these nested puddles and beautiful curving features. That's where the meltwater erosion was focused. And one of the things that sort of highlights that is this line of dark, rounded boulders in the low here. But then at the same time, these arrows are showing you these really angular boulders that are the same color as the local rock. So we've got a lot of plucking happening as well. So all three processes happening in one site. And what this site does is illustrate those sort of co-relationships between all the processes. But now that we've got LiDAR data that shows us excruciating detail on the land surface for virtually all of Ontario, we can start to identify a lot of other features that record these same sorts of things. So here's an example from eastern Ontario near, in between Renfrew and Cobden. And we see a lot of typical things like a moraine, nicely streamlined till and bedrock, and some beaches. But the striking feature here are these sinuous scars, these sinuous cracks in the central part of the image here. And these aren't meltwater channels, these aren't typical things. What we're actually seeing here is huge chunks of thick slabs of rock that are being pulled apart by the influence of ice shearing across that surface. So it's actually displacing the rock because there's no supporting rock downflow of it as the ice is flowing towards the bottom right of that image. The other side of that is when ice is flowing up against an obstacle, we see a lot of other signs of really focused erosion. So along this line, along the cross-section here, that central one in the box, which I'm showing, oh, now I've gone and messed things up. There we go. The central one here is showing you a really nice, huge rectangular feature. It's almost 12 meters deep, 1 kilometer wide, 2 kilometers long, where rock is being very preferentially eroded. And now, I'm not going to say that that was eroded at one time by one set and come out en masse, but at the same time, it could have. We see lots of increasing number of examples. This is from a quarry not too far away from that. Again, near, this is Eganville, Ontario, and that white dashed line at the top is showing a pretty interesting contact. When you zoom into it, I'll put the white line back on. That's showing you the base of 450 million year old limestone sitting on top of 20,000 year old till. So the ice has ripped off 6 meters of rock, about 2 soccer fields wide, and transported it some distance downflow. Then on top of just moving it, it's also created these large injection features where till is being forced up through the cracks in the rock, locally penetrating the entire succession. And in lots of areas, the pink lines or purple, whatever they're looking like, are showing intense zones of fracturing. So not only is it moving it, but it is absolutely badgering it up at the same time. And I'll argue that this is a bit of a special case, but essentially it's a really telltale sign of something called hydraulic jacking. And what this is essentially nature's version of fracking. These rocks have predisposed weaknesses. This is a nice sort of illustrative picture. The rocks have pre-existing weaknesses like joints and bedding plane discontinuity. And when meltwater pressure beneath the ice, when that meltwater builds up, it can only get increasingly pressurized if it doesn't have anywhere to go. And if there's enough ice on top, the pressure in the water can exceed the strength of the rock, and then that can create or dilate fractures during drainage events. And if you're lucky, sometimes those cracks get infilled with sediments, and that can have a major impact on the bulk permeability of that rock mass. So in some cases, if the ice remains active, it transports that material en masse, and we're seeing shear planes developed in the till as the huge raft was being dragged along the base. But that's a bit of a special case, because usually what happens is these huge blocks of rocks get essentially pulverized almost instantly. So this is a nice example from south central Ontario, north of Peterborough. You've got a nice bedrock limestone pavement at the bottom. And then you can see lots of blocks of nearly intact rock in the lower part. But then the upper part of that exposure is essentially just rubble tills, just these blocks of angular limestone, almost entirely limestone material. And so this is sort of what's probably more typical, and we see this on a regional scale. So this is an area of south central Ontario, kind of in between the Napanee limestone plain in the lower right and what used to be called Dummer Moraine in the sort of the upper left of the image. But with LiDAR data, again, we're seeing a lot more complexity. So it's not just a couple landforms here. It's this really complicated patchwork of meltwater deposited sand and gravel shown in orange, Canadian shield bedrock in the northeast. We've got these large, no, I can't get the laser pointer. The purple areas are showing other areas where the rock is being dragged and displaced en masse. And then the light green areas are areas where we've got this rubble till. And this area used to be called Dummer Moraine, but now we're seeing it's more likely representing a much different process. And the one thing I want to highlight with this image is that this is what the base of the subglacial bed looks like. This is a snapshot of how complex it is, but we almost never see it exposed like this because in so many areas, especially in southern Ontario, it's buried by 10, 20, 30, 50 meters of younger sediment. So we're only seeing it in boreholes or in geophysical profiles, but this is the complexity that we're dealing with. So all the pictures I've shown so far are shown on this map in the stars. And the one common thing you might notice is that there's a very close association between where rock is behaving badly and the presence of inferred or known karst conditions. And the other thing you might notice is that all the big polygons, similar to what Abigail just showed you, are showing you where our three-dimensional groundwater projects are, and you might notice that those are also covering areas of known or potential karst. And so with Ashok Shah and Emmanuel Arnaud at the University of Guelph, we've started taking this new understanding and looking back at boreholes that we've drilled in the past. And so that's sort of the next phase of this talk. We're going to quickly go through some pictures and show you what this looks like where we can't actually see it in outcrop, but taking this new knowledge to hopefully understand things a little bit better. So here's an example from the Brantford-Woodstock area. The orange arrows are showing you fractured areas that aren't mechanical fractures from drilling. These are potentially things that the glacier did itself, as well as a thick zone, 10 centimeters thick, well below the bedrock contact, where we've got injection of till well down into the rock layers. Here's an example from Simcoe County in shale bedrock below the Niagara Escarpment. Again, orange arrows are showing you fractures, green arrows are showing you fractures that have been infilled with this till, and the red arrows are showing you larger zones where diamict is infilling gaps. And this is just a highlight of one larger sediment infill fracture that's about 60 centimeters thick, well below the bedrock contact. Another example from Niagara. This is a pretty interesting one because you've got this reddish-brown till overlying essentially a dark gray and light gray bedrock. And so there's very little relationship between the till and the underlying rock right below it. And then also the material that's been injected in between the competent parts of the rock is, again, not related to the rock at all. It's coming from the till. So something foreign is being injected by the ice and influencing the rock itself. Here's an example from Guelph, from Abigail's drilling last fall. And this one's interesting. The two colors of boxes are showing you two different facies of till that have been injected, suggesting that there are multiple events. This wasn't a single pulse. This is happening multiple times, potentially during multiple glaciations. And then another example, just highlighting again some of the extents and depths that this deformation or this sort of disruption of the rock is occurring at. But then I'll also, just like the last slide, the purple arrows here are showing you fractures that have been fused by either calcite or gypsum cement. So again, multiple phases of this are happening, and then sometimes they get fused back up. So we're creating preferential pathways for water and sediment to be injected into the rock. And there's the animations to go with that, sorry. And then the last example is from a shale bedrock setting in what was a reentrant valley into the Onondaga Escarpment. Nearby water well logs showed a lot of gravel, so the thought was that we were going to get into a subglacial gravel that was deposited by the ice as it was flowing over the escarpment here. But the drilling, which would not have been fun at all, found a lot of zones of just material that has been injected down into the bedrock. If you look at the scale cards, we're going from 12.25 meters down to 21.25 meters. So we're going 9 meters down into the bedrock, and you're still not in anything close to what you would call competent bedrock. And to the point where there's actually discrete water flow zones based on significant water loss and mud loss during the drilling, you've got these sort of multiple stacked shale aquifers in this setting because of how much the glaciers are bulldozing and kind of ruining that normal rock. So this is a map showing the locations of all of our projects and all of our boreholes. And I'll just highlight that the green ones are showing so far the ones that we've studied that have a signal of this hydrofracturing of wrecking the bedrock. And the white ones are showing ones we studied where the rock underneath the glacial deposits are intact. The smaller black dots ones are ones we haven't visited yet, but it's just giving you a rough sense of the scale of how pervasive these conditions actually are. And the reason that's important is because that interface is often a really important flow zone. And it's always typically been attributed to the idea that that upper surface of rock is a little bit more fractured or has a little bit more permeability. But really, what is the interface and why does it have those characteristics is ultimately what we're trying to better understand through this project. And so this is just a very difficult to read water well record, but it just really illustrates the point here. You've got 17 feet of hard, dense clay stones, which is probably till, and then that overlies the succession of rock, which is shattered limestone, and then you get another 20 feet of hard crystalline limestone, and then another 20 feet of badly broken weathered limestone with 2 to 4 inch weathered layers that the driller tried for 3 hours to keep open and just gave up because they were losing too much. So a few years ago, something like this we would have probably looked at with a really cautious eye, but now that we're seeing rafts of rock 6, 8, 10 meters thick, the range of possibilities for what we would consider okay in the water well records is expanding significantly. And the other thing I want to highlight out is the potential glacial influence on regional permeability of rock layers. So this is, again, our karst map and locations of provincial groundwater monitoring network wells. And the open polygons in the dark colored are showing areas of interpreted enhanced recharge based on Stu Hamilton and Frank Brunton and Liz Preeb's work, looking at the geochemistry of the waters. But you'll notice that a lot of those polygons are covering areas that aren't associated with known karst conditions. And I would suggest, based on what we've been seeing, that there's a missing link, and that's the glaciers and their subglacial processes that are influencing the, increasing the permeability of these rocks. And just as a final note, if you displace these rocks enough, you can create really troublesome conditions. This is a picture from beneath the downtown area of Montreal, where the rocks have been separated enough and then been flushed with meltwater to the point where there's significant cave systems that are operating. And this is something that potentially need to be watching out for in Ontario, because we're seeing the exact same sets of processes operating on regional scales. So to wrap up, I've kind of talked about the different influences we're seeing in terms of glacial and bedrock interactions. It's just something I thought I would highlight here today as something that might expand our consideration for what is normal. And hopefully I've sort of at least got you guys to think a little bit more about what is competent bedrock and what are the range of possibilities that we're going to see as we drill down from sediments into the underlying bedrock. So there's just a quick hit with some of the references cited here. And I don't know what I'm doing for time, but I will wrap it up. And if there's questions or you guys have similar examples, please find me. I'm sitting over here, and I'd be more than happy to talk more about this stuff. Thank you very much.
Thanks, Riley.